流动based method. Let's first review some Newton method. Now consider the non-linear equation. Assume x star is a root. This equation. That means f(x star) is equal to 0. Now we are give a approximation to this root. It's like this. The Newton formula is the Newton Raphson formula is that x star is equal to x minus f tilde f pi f tilde. This is a Newton formula. We know this is improved approximation. Usually, this is better than this one. We draw a picture. You see that. This is x, y. If we have v equal to fx, this is just the root. We have a approximation. Suppose it's here. Here is x. So this point we have a tangent line. This is a tangent line. Then this x hat is just here. For this example, you see this is much better than this one. This is Newton method. It's if the x this is very near this one will be converging very quickly. This is a Newton method. But this formula is not easy to extend to the matrix problem. Just for our eigenvalue problem, it's not easy to use. We can try this formula in other way. For example, we consider a simple example. We want to find the square root of a for some a is positive for this one. You know, it is to know this one is just equal to serving this equal to this one. It's just equivalent to this one. This is the fx. So we have the Newton correction is this way. Fx pi fx just equal to x is pi is this one. Now we derive this formula in either way. We write this x plus x1 plus x cubed plus d is square just if this d, because x1 is approximation to the root, so it's d is very small. D is small. We extend it, we get x square plus equal to a. If this is very smaller, this one may be much more smaller. So we can drop this term to get x cubed square 2d x cubed just approximates to a. So we get d is approximate a minus x squared. This is just the same as this one. This is a simple way. This process, we get this formula. This process is easy to extend to the matrix problem. Next, we use this process to give the Newton formula for the eigenvalue problem. Now, Newton method. Now we assume that x with mu z approximate eigenpower our a, assume this is a null. We want to find ways to determine under and y, so that mu plus under z plus y is a improved eigenpair approximation. We hope this is better than this one. This is our goal. Now, similar this way, we assume now we let mu plus and hat z plus v hat is a exact eigenpair of A like this. That is A plus z m times this is equal to and we get this just like this equation. Now we expand this one. We get az plus a with hat mu z plus mu v hat under hat z plus under v hat. No, this is just like this one. So, if this is much better, is a better approximation eigenvalue of this matrix. So, this one should be smaller. This one is also smaller. So, this is much better, much smaller. So we take like this, we drop this term. We get approximate. So you have this is this is no, A is no, Z is no. This is also no. But this have unknown. So we get this A minus mu I, we had minus under is just equal approximate to A Z minus mu Z. This is just the residual. So this, if this is exact eigenpair, it will approximate this one. So we find the under mu to satisfy this. So define the correction to be the solution. To the following system. Just is A minus mu I V minus under Z is equal to R minus R. This is just like this, the correction is just this one. So we want to determine under way is just to satisfy this. But you see, this system has n equations. But this is v is n-dimensional vector. This is also I know. So they have n plus 1 I know. I know. So this system is underdetermined. In order to this have a unique solution, we must add another equation. So we can add an equation as just this one. We hope that v is equal to 0. This is just equivalent to that one. This is this z plus y is equal to 1. Sorry, here we must make some assume first. This place here. We assume the mu, the z is unit, length is just 1. Then the mu is just equal to the really quotient as to condition. Just the approach eigenpair is satisfy this condition. So use this one, you know that this is equal to just that means the improved eigenvector should be satisfy this condition. That is this meaning. In matrix form, we can write this in the following. In matrix form, it's just A minus mu I z star 0 v under should be here is minus equal to minus R0. In matrix form, it's just this 2. Right in matrix form is just this way. So we can solve this system to get the solution. How to solve it? Just use the Gauss elimination. We multiply it from this side, this matrix. Here I 0 minus z star A minus mu I inverse. If we multiply this matrix from this side, we get this zone is due to chance, but this gets 0. This is just this A minus mu I minus z为 n 大。This is just equal to, this is not changed. This is changed into just this way. We just multiply from this side to get this one. This is become 0. So this is a triagonal, triagonal system. So we can, from this last one, we get n is equal to this star a minus mu z is this star a mu r. This is the solution of the n dot. Then from this we get the v is just equal to this one. Move that way. The food a minus mu I ni r is minus under z. So we get the way under. From this we can compute a number. Then institute into there. Then we get the y. So that is Newton correction. We get this two y is scalar, y is vector. This is in general is better approach the eigenvalue than this one. This is a Newton method. So this is we call the Newton correct formula. Newton correction formula. This is two, just so that is this is the Newton method for solve the eigenvalue problem. We get the correct formula. But this formula is not easy to extend to other methods, so we need to give other representation for this formula. So next we will do that. We hope to eliminate this number. So the next we give the Newton correction equation. Our goal is to give an alternative. This formula old EigenValue old y. This is our goal for this one. The method is get this is use some projection method. To get this alternative. Now let's to do this, let P is equal to I minus Z star. This star. Wait. This is just you can say this is a projector on to the also normal orthogonal sorry orthogonal complement over Z, just as this one. Y is this subspace. This is a projector, or this is subspace. For this projector, we have the following properties. First, the P, if PR is just equal to R. 2 PZ is just equal to 0. 3 is PZ, PV is equal to V. This is 3 simple properties. That is easy to verify. For example, this one, we can see this one. That's a PR is just equal to I minus Z star times R is equal to R minus Z star R. This one. The R is equal to AZ minus mu Z. So Z star R is just equal to Z star A Z minus mu Z star Z. We have assumed that this is equal to 1. This is just mu. So this is mu minus mu equal to 0. So this is 0. So this is just equal to R. So that is very simple. Now, we use this property, we get for this equation, we get P A minus mu V plus minus P Z equal to P for P R multiply P from the left. This is equation. This is just equal to R because this is equal to 0. So this term is equal to 0. Then we use this properties. So we got PA minus mu I, PY is equal to R. It doesn't involve the, it doesn't need the end. We get this one. Use this is just some symmetric. If A is symmetric, this matrix is symmetric still. So we use this one. Now the second equation, this is just equal to V must orthogonal to the Z. So we got the equation. This equation is just we call the Newton correction equation. Equation, just this one. If we call this is 3.1, this is 3.2, we have the following result. V is satisfy (3.1) if add only if we satisfy the 3.2. That means if V is defined in this way, we know that this two number must satisfy these two equations. From these two equations, we just derive this equation. So if we satisfy this, must satisfy this. That is very simple. Now is only needed to prove this things. This we suppose the way is satisfy 3.2. This one. We have we got just is I minus z star is A minus mu I z star, or y is equal to R. Just this one. Because this things, so this is just equal to I z star A minus mu I is y is equal to R. Just this one. So we have A minus mu I y. This is equal to R plus z star A minus mu I y. This is moving into this side. We get this. This is a vector. This is a vector. This is inner product. So this is a number. We define it as alpha. It's just some scalar. So we have A minus mu I y is equal to alpha z. This form. You see, you must satisfy this condition. So we have from here we get V is equal to A mu I R minus alpha Z. Then Z star V is equal to 0, just equal to this A Z star A minus mu I minus R plus alpha Z star A minus mu I Z. From here we get the alpha just equal to Z star A minus mu I, Z star A minus mu I R. This is just equal to this under. So this is just the solution, this one. So we know we satisfy. .1. That is the result. So we can use this. You can use this one as a Newton correction formula. Also, you can use this Newton correction equation to do some things. This two is equivalent. So sometimes use this is very convenient. Next week we see that this things. We will next we will give use this result. We just want to give another very interesting method. It's just this. Jacobi derivation method. This method is what used just get this method from the Newton method. We talk the Newton method just in order to get this method. This method is the Newton correction equation combined with the real Leeds method proceeds. We get the Jacobi derivation method. In other words, the Jacobi derivation method just is this two method combination of these two methods. So the Jacobi derivation is just like this. So now is we could get the basic Jacobi derivation method algorithm. We have the first way. Matrix V is just equal to a vector. The V is belong to the C with the number is just equal to V E1. This is just the start vector. Just to start vector. Then we K from 1 to K max. This is given positive integer. Then we use we compute a normalized with pair. Mu z such that mu is near tau. For is R is just equal to A z minus mu z, the residual. Then if R is sufficiently smaller, we return mu z at the ext. 6 to a shift kappa near tau or mu. 7 serve the correction equation. This one, A minus kappa I this down. We is just equal to add then also normalize the way with respect with respect to y 乃为 at signal non-convergence. We just say some little things about this algorithm. We use the Newton method to get some orthogonal matrix V. Use V, we get some space, subspace. This space is just R V. The V is just equal to, this is defined like this way. V equal to V minus X. X belong to, if this is N bar K. We use K. So this is C is K. This is subspace. This space is this. If V is this Y, K. This columns form also normal basis for this subspace. But this subspace just use the Newton method to get the every vector. Because we solve this Newton correct equation. First is 1 dimension, then second is 2 dimension, then K max is the maximal dimension. So the K max should the K max do not greater than N, must satisfy this. So here is neither method. We use this subspace, then use the really rich method to get some eigenvalue. It's just use Y. It's in fact it's just get matrix V star A V. Then to compute eigenvalue and eigenvector. Try Y is near to this tau. So the tau is a given number. This number is setter. The setter of a focal region in which we wish to find the eigenpair. That is mean we first know which region is we will be what to find the eigenpair. For example, we know the tau. We just want for this region we want to find some eigenpairs. So this is you must give. In the before the algorithm, you must know that number, focus number. This kappa is a shift. Shift. It's used to the kappa is just equal to tau or mu. If you take kappa is tau, this equation may be simple. It's the kappa is not charged. Every step is same. So this for equation may be very simple. But if you take kappa is mu, the mu will charged every step because it is eigen rate value. So you must charge. So every step you must solve the different systems. So that is the different. But if you take kappa is equal to mu, you can prove this method is converging quadratically. So convergence is very quick. So that is the advantage. This is all used to speed up the algorithm convergence. So here is several things. This is very different the lateral quadratic subspace method. The difference is the subspace is not the same. This is just use another subspace, not use the quadratic subspace. The space is use the Newton method to get the basis of the subspace. The idea is different. Mainly, this subspace is use just use the matrix vector product to produce the subspace. But this is use the Newton method to produce the basis. So that is another kind. So this method also can be used to compute with a large used to compute few compute one eigenpair over a large sparse matrix. This kind of matrix, large scale. Just compute one, you should know. There are another things needed to see. How to solve this system? You must solve it. Here did not say how to solve this equation. This equation has some technique to solve it. If we have time, we talk it. If we have no time, I will do that. Now we 10 minutes break. Just